Welcome to qnawire.
In this problem, we have a closed feed water heater here. And so we have water coming in here, and it is getting heated up from the steam coming in here. And so this is probably coming from a pump being put into a heat exchanger, but there's no mixing in here. There's just conductive heat transfer between the two liquids that are in, on separate pipes. We have a pump here that is then takes the steam and pumps it up to the pressure so that they can combine. So at 1, 2, and 6, the pressures are 7 megapascals, and then at 3 and also 4, the pressures are 6 megapascals. So um, so let's see here. We know that temperature at 3 is 325 degrees C. We have saturated liquid here. The temperature here coming in is 260 degrees C, and we're just basically going to assume a mass flow rate of 1 kilogram. So what we can do here is then we can let's see here. We can get the enthalpy at 1. Okay, so we have a saturated liquid coming in there, and we know that it at the with the pressure that we have. So we can get the enthalpy, and then let's see here. So is that 1? Yeah. And then at 3, we know pressure and temperature, so we can get enthalpy. And at 6, we know pressure and saturation, so we can get enthalpy. Yeah, so this would be coming from the condenser, all right? Or from probably actually from another pump because it's pretty high pressure. I'm not sure what the rest of the system looks like, but anyway, this is what we have or we given. And so we can do a control, a control volume around this whole thing. So we have coming in, the energy flow going in must be the energy flow going out. And likewise, at this junction here, the mass flow coming in at 2 and at 5 must equal that going out at 6. So we have the energy coming in has to be, the rate of energy coming in has to be the same as the rate of energy going out. So this control volume here, we have coming in the enthalpy flow at 1, the enthalpy flow at 3, then the specific work times the mass flow rate at 3, okay, which is be the same as at 4 and at 5. Mass flow rates here are the same too. Then let's see here. Then we have the enthalpy going out is the enthalpy flow at 6, and using our mass conservation, and also knowing that let's see here. M2 is the same as M1, and M5 is the same as M3. Okay. So now we can, let's see here, we can just solve this for M3 dot. So we have the mass flow rate at 3 is equals the mass flow rate at 1, and then this change in enthalpy divided by this change in enthalpy, and then plus the power, the specific power or specific work done for the pump, which we can find that because we can, at 4, we know that it is they said it was saturated liquid at 4. So we know that the I guess I should write that in here. So at x4 we have 0. So then we know the pressure at 4, which is the same as the pressure at 3. So we know then we can get the enthalpy at 4. And at 5, we know the pressure at 5 has to be the same as the pressure at 6 and at 2. So we know the pressure at 5 has to be the pressure at 6. So we got the pressure. And then let's see, what did we want? States at 5. And so at 5, we also have a saturated liquid. So approximately a saturated liquid. It's not going to make much of a difference whether it's kind of supercooled or not. So we can get the specific volume at 4, which is the same as the specific volume at 5. And then the pressure difference we know is 1 megapascal. And so we can get the work done. The specific work going into the pump is 1.319 kilojoules per kilogram. Plug that into here and then plug all of our enthalpies that we found in. And we get that if we have M1 is 1 kilogram per second, then we have M3 needs to be 0.0779 kilograms per second. So again, we don't need much coming in at 3 for whatever is coming in at 1. So basically a little bit of steam can heat this a lot, heat this quite a bit. So let's see here. That's I think that's about it for this problem.